Okay, hi everyone. Here's another video. So this video is going to introduce the concept of finding the potential for or near some charge distribution that's continuous. So we've calculated potential before. The result that's going to be most useful for us now is to recall that if I have a point charge, let's say I have a point charge Q right here, call that Q. Then at some point out here, let me call this out here. This is some point P in space, a distance R away from the charge. The potential at that spot is just equal to KQ over R. And that's a result we derive by integrating the electric field for a point charge. And the convention here is that the potential at infinity is equal to 0. That was our choice of convention. So when we say potential function, what we really mean is the potential difference between infinity and the point that we're considering. So that's something to keep in mind. But at this point, we're just going to talk about the potential at some point in space, and it will be implied that the potential is 0 at infinity unless otherwise specified. So that result's important to us because if we wanted to consider a continuous charge distribution, let's say there's some weirdo charge distribution that looks like this, like that, of arbitrary shape. A question that I could ask is, what's the potential at some point out here? So if there's some point P in space out here, what's the potential at that point? And this is a question that's similar to questions we've asked before. We've done things like asked, what's the electric field at that point in space? And the approach for potential will kind of go the same way. So let's imagine that we split up our continuous charge distribution into a bunch of tiny little infinitesimal charges. So let's say at some point right here, I have some tiny bit of this object, and that tiny bit of the object has some amount of charge, dq. And that amount of charge is so small that I can treat it effectively as a point charge. And if I do that, then I can say that, so there's some sort of radius distance from that dq to the point I'm considering, and I'll call that r. And if I do that, then I can say that the little bit of potential that's contributed by this little bit of dq is dv is k times dq over r. So I just treat that infinitesimal bit of charge as a point charge. And I get a little bit of potential contribution when I imagine bringing or moving along a path from infinity to that point P. There's a little bit of potential that I get from dq. And then, like with other problems of this sort, or when we did electric field, what we want to do if we want to get the potential will be integrating all of those dv's over the entire object. So that's going to look something like integrating k dq over r, and these integrals are over the entire object. Okay, so that's fine, but I wanted to work some examples so you could see how this kind of works in practice. In some ways, it's similar to doing it for electric field or for center of mass or something similar, like where we split objects into tiny infinitesimal pieces and then integrate over all of those pieces. But in some ways, it's different because potential is a scalar quantity. And that makes certain parts about this easier. And let me show you how with this first example. So let's do our first example. That's going to be finding the potential at the center of a charged ring. So let me scroll down here. And I'll leave this, this thing up. So here's 2. Example, potential at center of a charged ring. Okay, so what does that look like? That looks like I've got a ring, and the ring looks like this. It's a ring, not a disc, so there's no area here. It's just a one-dimensional ring looped into a circle. And I'm going to give this some radius. So radius r. Okay, and I want to know what the potential is at the center. So at this point, at the center, what's the potential? Oops, not zero. V equals question mark. That's the question. So how do I do this? What I want to do is I want to do this integral that I set up in the first part. So I want to calculate the integral k dq over r for every little dq in this object. So I can imagine that each dq represents, like if I take a little bit of length here, some little bit of length, that little bit of length has a little bit of charge, dq. And I can, because I want to integrate over the entire object, I really want to turn dq into a spatial variable. So really what I want to say is that there's a relationship between dq and what I'll call dl, which is how long this little infinitesimal piece of the ring is. So the relationship between how much charge there is and how long it is involves the charge density. So as with the electric field problems, I can break up my dqs into lambda, which is the charge density, times dl. And I'll say that lambda here, let's say this is a uniform ring. So uniform ring, which means charge density, lambda is constant. And in this case, because it's a ring, I know that the charge density has to be sort of the total charge of the ring, which I'll call big Q, over the length of the ring, which is just its circumference, so 2 pi r. So that'll be useful for us in a little bit, but not immediately. So, okay, what else do I need to know? I need to know for each little dq, how far away is it from the point I'm considering? For us, for the little dq that I have looked at here, that is a distance big R away from the center of the sphere. So I'll draw that in. So my little r in this expression is actually big R, because I've got every little dq here is the same distance away from the center, which is just the radius of this circle. So that's kind of nice. So let me plug some stuff in and we can start seeing how we're going to approach this integral. So v is this integral, k dq over little r. But we know some things now. We know that we could write dq as lambda dl. And we know that little r is just big R for every dq. So that's a constant, which is kind of nice. And if I'm integrating dl around this entire loop, I know I have to integrate from, say, 0 to 2 pi r, because I start at some point and I end a distance 2 pi r later. And this means that I can pull a bunch of stuff out of this integral. K lambda over r, those are all constants. So this becomes k lambda over r integral 0 to 2 pi r dl. If I integrate dl around the entire ring, I just get 2 pi r, which is kind of nice. So k lambda over r times 2 pi r. The r's cancel here. So the potential is just k lambda times 2 pi. That's the potential. I can do something else here too. I can plug in the expression from lambda into this. So if I scroll down, then I can write the potential as, now plugging in for lambda. Lambda is here, just the total charge over the total length. So then I get 2 pi times k times lambda, which is q over 2 pi r. The 2 pi's cancel. That's nice. And you can see that the result is, looks kind of familiar. It's just kq over r. That's kind of a cool result. That looks like a point charge result. So how do we interpret that? Well, the interpretation here is that it sort of is a point charge in a sense, because the point we've chosen is the same distance from every part on the ring. And when you have that, then you can really, you're just adding up the contributions from a bunch of point charges that are all the same distance away. So it's really just as if you're looking at kq over r for the entire charge. So that's kind of cool. That's a pretty nice and clean result. One thing I want to point out here, though, is that what was a lot easier about finding the potential here than had we tried to do the electric field is that the electric field's a vector and the potential is a scalar. At no point did we have to consider the direction of anything. Because the potential is a scalar, it doesn't matter where your dq is, it's still contributing the same potential to the center. Whereas if this was electric field, we'd really have to consider the direction. If we wanted to find the electric field for this ring at the center, that would have to be 0. It would definitely be 0 because the pull of every little dq on different sides of this ring would all cancel out. We'd really have to consider the direction. But here we don't. And that's one of the nice features of potential, or doing these integrals with potential, which is a little bit easier than with electric field. Okay, let's do a slightly different example. So my third example that I want is, maybe I'll start a new sheet for this one. So the third example that I want is the potential above the center of a uniform disk of charge. I guess charged disk. So what does that look like? That looks like this. Here's the disk. And that's supposed to be like flat in sort of like coming into and out of the page, if that makes sense. And then the point I'm going to draw right above it is up here, point P. And we'll say point P is a distance, what do I want to call that? A distance X above the top. And then we'll give the disk some radius too, and call that big R. The question we want to answer is, what's the potential at this spot up here at point P? V equals question mark again. Okay, so what we want to do again is we want to find the potential at that point P. So we're trying to do this integral again, integral k dq over little r. So we need to figure out what dq's we're talking about and what little r is for each of those dq's, and then integrate over the entire disk to get that. So I'll draw a dq here. dq now is going to have, so here's a dq, let's say. So dq has a little bit of area. I guess I was doing green last time, so let me do green again. So this is dq. And dq has a little bit of area in this case. It's a little bit of area on this disk. So I'll write this as dq is the charge density of the disk times the area, that little infinitesimal area of the disk. And again, let me say that this is a uniform disk. So uniform charge density So that means that sigma is equal to the total charge, which I'll call big Q again, over the area of the disk, which is pi r squared. Okay, and we'll use that again later when we sort of write our answer in its final form, but for now, we won't need it. But what's dA? Well, there's a couple ways to think about what dA is. One is dA is just sort of the area of this little rectangle that we've drawn here. So this little rectangle has two sides, and we want the area of that little rectangle. This side length just comes sort of radially outward from the center. So that's sort of the change in the radius here. So that side length is dr. And then this side length here is a little bit of arc length as we rotate around the disk. So that little arc length will be the distance that we are away from the center. And let's call that little r. No, wait, what do I want to call this? Let me call that A to distinguish it from little r, because little r means something specific in our calculation. That's A. So the arc length of this side right here, that will be A times d theta. So there's a little bit of area, or a little bit of angle swept out in that area, and the length of that side that goes sort of around the circle will be just the little a times d theta. So I can write that this way. So dA will be dr, that's one side length, times r d theta, that's the other side length. You can see this another way. I know we've done this argument multiple times, but just to make it totally explicit. If I have a top-down view of that circle, of that disk, then what we're talking about here is I've got a little distance a out from the center, and my dA looks like this here. And I guess let me redraw my A here. So really what I'm talking about is I've got some distance from the center, and there's some little d theta in there, so that there is an arc length that corresponds with the side length right here. That side length is a d theta. And then, so that side length is a, oops, looks like a d, a d theta. And that side length is just sort of like a little change in the radius, so that's dr. We'll call that dr. Really, should I be calling these DAs? Oh, I see I screwed up before. Up here, wait, let me point this out. So I screwed up here because really what I'm doing is little r here is really A, isn't it? So I want to erase this and rewrite it. So it's not dA, and it's not dr, it's dA, and it's not r, it's a. So I really want to write that as dA, little a, times a d theta. And down here too, it's not dr, it's dA. Well, hopefully that wasn't too confusing. I just want to make sure all my variables only refer to one thing. Okay, so let's think about how to do this then. What is little r is the distance. I need a different color now. What is little r is okay, wait a minute. Let me get organized here. So I need to redraw my x on the other side. So what is little r is this distance from there to there. That's little r, because that's how far dq is from the point we're considering, where we want to find the potential. But we've drawn a little triangle here. So r will be equal to the square root of x squared plus a squared. All right? Okay, so let's plug a bunch of stuff in. If we want to find the potential, then we're integrating k dq over little r over the entire disk, but we can plug a bunch of stuff in. So that's k, and then dq is sigma, and then I'll write a d theta dA over, and little r is x squared plus a squared. And then, so we actually have a double integral here. So we need to think about the bounds of two integrals. So our a integral should go from 0 to big R, and our theta integral should go from 0 to 2 pi. So we're going all the way around the ring azimuthally, all the way around an angle, and we're going out from the center where the radius is 0 all the way out to where the radius is big R. So that's the integral we need to do. And the integral looks pretty hairy, but it's actually not, because you'll notice that there's, in the denominator, there's this a squared under the radical, but there's also a factor of a up top. So if you imagine sort of doing an antiderivative here, the a here is the thing that would come out when you take a derivative of something that looks like this. So let's see how this would work out. So if I pull out a bunch of constant stuff, the k and the sigma are constant, and I'll write v as k sigma, and then I've got two integrals, 0 to 2 pi, and 0 to big R of a d theta dA over square root x squared plus a squared. I can do the theta part first. That's a pretty simple integral. For the theta integral, everything else is constant except for the d theta. So really all I'm getting is theta when I do that integral, and theta goes from 0 to 2 pi. So I just get a factor of 2 pi on this integral from the theta integral. So I'll write that and just pull it out from 2. So 2 pi k sigma. Now I have a single integral 0 to r, a dA over square root x squared plus a squared. Okay, so at this point, you can do a u substitution if you want. I'm just going to try to do it off the top of my head, and you guys can check me. So if I imagine taking an antiderivative here, I'll keep all the constant factors out front. And what I really would have would be just something that looks like this, x squared plus a squared, evaluated from 0 to r. So how does that work out? Because if I took a derivative of this expression that I just wrote down, then it's a chain rule. So there's an outside function, which is the square root. And if I take the derivative of something that's to the 1/2, then it goes minus 1 power to the minus 1/2. So I end up with this in the denominator when I take a derivative. But also I would get a factor of 1/2 that comes out front. But that's canceled out by the factor of 2a that I get coming out from the inside when I do the chain rule. So that's what gives me just the a up top here in the integral expression. And you can do that with a u substitution too, if you want to check my work. But for now, I'll just leave it there and hope that you trust me and hope that I didn't screw up. So let me plug in the bounds, or evaluate the bounds. So 2 pi k sigma, and then the upper bound is square root x squared plus r squared, and the lower bound is just square root x squared plus 0 squared. Okay, so then v is 2 pi k sigma square root x squared plus r squared minus x. Okay, that's cool. I can plug in sigma too here. So sigma was just the total charge over the area of the disk. So if I do that, then I get 2 pi k total charge over the area of the disk, pi r squared, times square root x squared plus r squared minus x. Okay, that's kind of a cool result. Is there anything else to do there? I guess we can cancel a factor of pi, right? So we can cancel a factor of pi. And then write sort of a final form as 2kq over r squared times this square root stuff minus x. That's a result. And we can talk about the interpretation more if you'd like, but I'll just leave this result here for now, just as an example. So I hope that helped introduce how you find potentials for continuous charge distributions, and we'll do another example in class next time. I will see you guys soon. Bye.